the research that Nicolò and I are doing starts from this kind of simple fact. If we ask the question, how do mathematicians make mathematical discoveries? Well, the answer cannot ignore the role of analogies. Right. So, in a sense, the role of analogy in science has been widely discussed. We are sort of pointing out also the role of this inductive way of thinking, analogical way of thinking in mathematics as well. And to show this, to display this role of mathematics in mathematical research, here we have a slide on André Weil in his correspondence with the sister Simone Weil, the famous French philosopher. So this is a wonderful correspondence between the two that I recommend you to read if you haven't done so yet. In Italy, it's available in a little book. It's about 100 pages. And I think sort of summaries or kind of excerpts from this correspondence are also available in English translation in an article in the American Mathematical Society. So if you're interested about analogy, this is a wonderful piece to read, because what happens is basically Simone Weil is asking André Weil to kind of discuss or to describe his work as a mathematician to somebody who's not a mathematician, and André Weil tries to come up with an explanation of his research. And in this explanation, analogy turns out to play a rather prominent role. André Weil says, for instance, Artin functions in an abelian case are polynomials, which one can express by saying that these fields furnish a simplified model of what happens in number fields. Here, there is thus room to conjecture that the non-abelian Artin function are still polynomials. That is just what occupies me at the moment. Right. So this is a summary of a research project that André Weil famously pursued, and that basically brought about the proof of an analog of the so-called Riemann hypothesis, an important hypothesis in number theory. As Weil elaborates, in fact, nothing is more fecund in mathematical research than this slightly adulterous relationships, by which he means the sort of relationship of analogy between distinct mathematical domains. And nothing gives greater pleasure to the connoisseur. All right. The way Nicolò and I approach this topic of analogy and mathematics is from the perspective of epistemology. So it's a distinctly philosophical perspective rather than an empirical one. From the perspective of epistemology, the crucial question has to do with trying to understand how analogy contributes to the knowledge in the mathematical domain. So more specifically, the problem can be seen as finding, on the one hand, the implicit norms of what constitutes good analogical reasoning in the discipline of mathematics, and to at least outline an epistemological story that can justify the use of analogical reasoning in mathematics. Or at the very least, it clarifies whether and how the use of such reasoning, such inductive reasoning, can be justified in mathematical research and for mathematical discovery. So on this, we have on these issues, we have two recently published or forthcoming articles. One of them was just published a few days ago after a long period of review. This is our reasoning by analogy mathematical practice, and now another paper together with our colleague Katerina Sisti is forthcoming in Erkenntnis with the title Confirming Mathematical Conjectures by Analogy. Well, you know, like I encourage you to obviously read the paper, and hopefully you read the papers and hopefully you like them and you'll cite them. But today we want to do something that is a little more courageous, if you like, a little more more brave. We want to branch out and sort of talk a bit about the bearing of this epistemological study on the disciplines of psychology and pedagogy. Okay, so the aim here is not to sort of be in our own territory, in the epistemological territory, but kind of move further away. The stuff that we'll present will be kind of sketchy and provisional in some way, but hopefully you'll enjoy the way in which, as epistemologists and as a mathematician, here we we confront ourselves with this sort of underexplored territories for us. Okay, so we're going to talk in particular about two topics. That is the relation of epistemology with psychology. So this is the first part of the presentation, and then Nicolò is going to focus on the relation of philosophical theory with pedagogical practice. Okay. So as I said, as I mentioned, this is sort of new territory for us that we're still exploring. So we will not present any sort of new finding on the topic. We haven't even performed any experiments yet on the subject. The idea is we thought we'd use this seminar to receive some feedback on our initial plans or ideas, and then to see whether you find this valuable, not valuable at all, or where do you see the value in this project. So I'm going to talk mostly about the relation of epistemology with psychology. And here, our target for this discussion will be a prominent paradigm in the psychology and cognitive science literature on analogy, which is the structure mapping approach developed in various works by Gentner. So on this approach, this approach attempts to discuss the role of analogy in science, but in ordinate reasoning more generally, by emphasizing the heuristic dimension of analogy in a dynamical process of reasoning. And it aims to identify the mechanism, the central mechanism in this sort of process as the recognition and the development of certain kinds of structural alignments between distinct domains, initially distinct domains. As we will see, it is a kind of an open question if the use of analogical reasoning in mathematics can be understood within this approach. With this in mind, we're then going to move to the relation of the philosophical and psychological theory with the pedagogical practice, because of course there's been a lot of pedagogy, pedagogical work inspired by the ideas of Gentner and others and colleagues on the processes of the psychological process of analogical reasoning. And so what we're going to see is that in a way, if the psychological theory is somewhat questionable on the side of mathematics, then also the pedagogical practice based on that theory may not survive criticism. So again, we emphasize here that we're not playing in the same sort of ballpark as Gentner. We don't have a kind of finding or discovery or empirical work that criticizes her approach. The idea is mostly to provoke, to raise questions, as it were, to make people think or reconsider some of the foundational matters in the discipline in an important paradigm in cognitive science. And for us, it's also an occasion to understand more about what people in cognitive science and in other disciplines are doing. Okay, so if the plan is clear, let me try to give a few examples of those that we mentioned in our research from the various examples that we use about analogical reasoning in mathematics. So let's start with a kind of a simple adaptation of an actual historical example of mathematical research, the discovery of the so-called Euler characteristic. Well, you know that in 2D, in convex polygons, the number of vertices and edges is the same. Okay, so that's simple fact to verify that vertices equals edges, V equals E for convex polygons. Now Euler comes in and asks if any similar regularity holds for convex polyhedra, right? For a cube, tetrahedra, and stuff like that. Well, the correct answer is number 2 is the so-called is that the so-called Euler characteristic is true. That is to say, the number of vertices minus the number of edges plus the number of faces is equal to 2. Okay, so that's the Euler characteristic. Now the problem is that, as it were, there may be 2 distinct ways, both sort of relying on analogy, by which somebody like an expert, a trained mathematician, might come to reach that correct conjecture, number 2. Okay, one of them, which was developed in the 1950s by Polya in this wonderful work on analogy and induction and in mathematics, probably you are all familiar with this, sort of develops a kind of an algebraic similarity between 2 and a kind of a slight manipulation of 1. Okay, so the idea is we rewrite 1 in such a way as to sort of make an interesting property of this equation emerge, which is the fact that it's a kind of an alternating sum of distinct elements, distinct geometrical elements of a convex polygon. And so by reflecting on this alternating sum of elements, and as it were adding the extra element of a solid, which we can represent with an S, we can sort of generalize from the 2D case to the 3D case to get the correct conclusion that in the 3D case, the correct relation that holds between the vertices, the edges, and the faces of a convex polyhedron is governed by equation 2. Okay, so this reasoning is based on a kind of an algebraic similarity in the alternating sum feature between between 2 and 1 star. Historically, however, this is not how the property of the Euler characteristic, which was conjectured by Euler but proved later, was arrived at. In fact, another kind of reasoning, a more geometrical reasoning, also involving analogy, was used. And this is the attempt at a proof, if you like, or the argument that was put forward by Cauchy, which employs, is again another different kind of analogy in a more geometrical way. The idea, roughly speaking, is that you take any convex polyhedron and you imagine smashing it or flattening it, right? So on this picture on the left, you have the case of a cube being flattened. Okay. Now, of course, some of the edges of this flattened cube may be elongated in the process, but that doesn't matter. The idea is to get to something that looks like a flattened sort of surface that we can reason with, right? And then from connecting some of the sort of the old edges of the smashed or the flattened cube, we can obtain sort of roughly triangular surfaces, like the one shaded in gray that you can find in this figure. And the idea is that we can verify that by removing some of these triangular surfaces in the cube case, for instance, the relation between the vertices and the edges of the resulting figures remains constant. All right, so no matter what kind of triangular surface we remove, the analog of the Euler characteristic, namely 1, remains true. So the relationship remains constant under this change of this removing of triangular surfaces, with the result that by thinking about the geometrical similarity that link the various kinds of regular polyhedra together, we may come to the conclusion that it's plausible, geometrically speaking, that the correct sort of relation between vertices, edges, and faces in a convex polyhedron is the one that is expressed by equation 2. Okay, so what we want to underline here is that we have two distinct arguments, both involving, in a way, similarity, in a case, a kind of algebraic similarity in the alternating sum feature, in the other case, a kind of more general similarity of regular polyhedra, right, in geometrical features. But this, this arguments are felt very differently, from a mathematician's perspective. In particular, it seems rather clear to us that the algebraic argument relies on a rather superficial algebraic similarity between 1 star and 2, whereas there is a sense in which the geometrical reasoning is sort of much stronger in comparison. Okay, so the point of the example, I guess, can be summarized in this way. Look, there's a lot of research in psychology, in cognitive science, that stresses correctly the role of the heuristic function of analogy in the dynamical process of reasoning. So you can see the student or the researcher as proposing different conjectures based on projections from various kinds of models. And so this is sort of the heuristic dimension of reasoning. But we think the heuristic function only tells a partial story about what the analogies mean for the working mathematician. Certainly many analogies involve schema abstraction, what Gettner will call schema abstraction, or shift our perception of a given target in the sense that the given target is re-represented in Gettner's sense. But there remains an important difference at the level of what the working mathematician feels between deeper and more superficial analogies in practice. Right. So there is a quote from there's an insight from Hadamard's work on the psychology of a mathematical discovery here, which is that mathematical training comes with developing a kind of discriminating capacity, whereby one is led to distinguish between certain kinds of mere hookings, suggestions, or hints, like the algebraic similarity that Polya has pointed out, and certain kinds of relay results, more significant discoveries, more deeper kind of similarities that are, for a mathematician, are more telling. Now, you might think that, this what we might call the Gettner style approach to to the psychology of analogical reasoning might be able to account for the sort of perceived differences in strength, as we tried to illustrate with the previous example, between distinct analogical arguments in mathematics, between mere hookings and relay results. For instance, if you recall in Gettner's account, there is, the account imposes certain conditions like the one-to-one correspondence of the predicates in each domain. There's a requirement of connectivity, whereby the predicates in each domain will have to have sort of the same arguments, and there is a further requirement of systematicity in the in determining, as it were, the plausibility of an analogy, right? So the idea is that we have a bias, as Gettner calls it, for deeper, more explanatory relations. So analogies based on just certain kinds of correlations, statistical correlations, so very slight correlation between distinct events, are not seen as plausible as analogies that instead indicate a certain kind of commonality in causal or explanatory structure, right? So where the relations that hold between the terms in each domain are sort of stronger or more important in some sense, right? So that's the requirement of systematicity. But the problem is that, at least we think that there's still a question open whether one-to-one correspondence, connectivity, and systematicity can actually account for this sort of the practice of telling apart superficial from deeper analogy in mathematical practice. Okay, so here we have another example that hopefully illustrates this. Of course, there's a lot of examples that we could use. We try to use certain kinds of intuitive ones, simple ones to get the intuitions going. But there's a lot of other examples we could have used if you're unconvinced by this. This is a case of inferring, again, a property of the 3D case from a model in the 2D case, the bidimensional case. And there's again a case in which we have two analogical arguments, as it were, for the given conclusion. The question roughly is, well, you know that sort of the three midpoints of the edges of a triangle. So if you draw a line from that to the opposite vertex, okay, so that the three medians, as it were, intersect in a common point that is called the barycenter. That's the red spot that you find on the top figure on the right of the triangle, right? Now the question is, can you generalize that to the 3D case and sort of infer from that 2D model that in the 3D case, the three medians of the four medians of the tetrahedron, that is to say, the point connecting the barycenter of each tetrahedron's face to the opposite vertex, also intersect in a common point. Okay, so the question is there such a unique red thing as you find in the bottom slide in the tetrahedron and the bottom part of the slide? Well, the correct answer is yes, but again, what we want to outline is different analogical arguments or different ways of getting analogically to the same conclusion. Okay, so one thing you could do is to consider roughly the problem from an analytic geometry perspective. And so defining, knowing that the medians of the tetrahedron are, the midpoints of a tetrahedron are identified as X, Y, Z on the slides, and knowing that the corresponding barycenters have a kind of similar analytical expression in the Cartesian coordinate system as X, Y, Z, and W, okay, you might infer that since there is such a thing as the barycenter in the 2D case, that the algebraically similar expressions in the 3D case will also concur in a center of mass, or in a barycenter for the tetrahedron. The other way of thinking about this is purely geometrical. That is to say, you start from the fact that, roughly speaking, the barycenter in the 2D case is a kind of a center of mass for the figure. It's an improper way of speaking, but it's a common way for the mathematician to sort of identify what's important in this geometrical property of the barycenter. And from that, and from the known kind of implicit geometrical similarities between triangles and tetrahedra, one could make it plausible that the tetrahedron too will have a single sort of center of mass. Okay, now again, this is just perhaps not the best examples in certain ways, but it's a very intuitive example to show that, again, relational structural alignment or relational structure seems to us insufficient to explain the difference in strength between the analytic geometry case and the pure geometry case. Again, we think that the reasoning is much stronger from the 2D case to the 3D case when considered in the pure geometry terms, that is the natural home of the problem, rather than using the Cartesian scaffolding that is the representation of the problem in the analytic terms. And notice that in a way, the structural alignment holds for both, right? There's a course, a kind of scheme abstraction, re-representation involved in both the analogical argument stemming from analytic geometry and the analogical argument stemming from pure geometry. The systematicity, as it were, seems to be satisfied for both. In fact, it's even worse because, well, you might know that the theorem that there is a barycenter in pure geometry stems from the so-called Chebas theorem, but there is no known analog of that theorem for the 3D case, right? So, in a sense, the analytic geometry is even more systematic than the pure geometry case, and yet the plausibility judgments go exactly the opposite way. Again, maybe not the example that you find most convincing, but the point that we're trying to make is rather simple, is that sort of structural alignment or relational sharing of relational structure does not immediately correlate with more plausibility. And that's a problem if the aim is just is among other things to try to explain some of the plausibility judgments that accompany analogical reasoning in mathematics. Okay, now maybe you can say, well, this psychological theory that we are criticizing here was never meant to give any such account as explaining, for instance, the high order judgments of mathematicians in research, doing research, or the phenomenology of analogical reasoning from the perspective of an insider, of a mathematician. But if that's right, then, well, two things. Then, first of all, this would show that the psychological theory is somewhat incomplete, that it needs to be completed with something like a philosophical theory that explains the norms of skilled, as it were, analogical reasoning in the discipline. And the other thing that is also important is that if that's right, that is to say, if it's true that sort of psychological theory was never meant to account for the high-level judgments and the difference, the intuitive difference between hookings and relayed results in mathematical practice, then that also questions the applicability of the psychological theory to pedagogical practice. The reason is roughly, well, what kind of skill are we trying to teach the students? Are we trying to teach something that looks like, good analogical reasoning from the perspective of, say, somebody working in the discipline, or are we trying to simply, as it were, prompt a kind of reasoning that is based on comparison?
Can I just ask a quick question, Francesco?
Yeah, sure.
Could you just explain a little bit more what you mean by plausibility judgment? Because I didn't.
Oh, yeah, sure. So we think that, in a way, the reason, the inferences that we have here, the analogical inferences that we have in the two examples that we gave, come with different plausibility, that is, or with different strength, if you like. Okay, so one analogy is deeper than another. One analogy sort of hits at something more important about the relation between, say, 2D and 3D than the other. And that means some of the inferences that we can draw from the deeper analogy are also going to be stronger or more plausible. Okay, so it's this difference in the strength of the analogical inference or the plausibility that we get at the end of the, in the conclusion, that is our concern here. Does that clarify?
Yeah, thank you.
Okay, good. So I wanted to briefly introduce also Nicolò's part by just briefly talking about the pedagogy part. Now, this is an area that we don't have a lot of expertise on, but we're trying to sort of recover quickly. The idea, as we understand it, is the following: that is, while teaching analogically or case-based learning is notoriously difficult. Students often fail to recall the examples that they have been exposed to. They often encode content in a kind of concrete situation rather than thinking about how to generalize that content to other situations. And really solid results only seem to be obtainable with highly trained students. So studies estimate at least 10 years of training to possess the relevant skill in doing correct and strong analogical reasoning. So the question whether we can accelerate that phenomenon is a live question, because it seems that we want to put the students in a condition to train in a way to be a better mathematician, a better scientist. Now, proposals have been advanced of, for instance, most prominently from Gentner, analogical encoding, progressive alignment proposals. These are very serious proposals based on a lot of empirical work to accelerate analogical reasoning and teaching by analogy. But again, the proposals seem to partly suffer from a certain idea of what good analogical reasoning consists in. One way of saying this is to say that, look, in a way, if for instance, take analogical encoding, which aims to present students with cases to compare and to find generalizations, or the proposal of progressive alignment, which purports to follow the sort of the natural development of a student from more superficial to more relational structure, more abstract similarities. Well, the problem remains that, as we try to illustrate with the previous examples, that not all of these abstract similarities, or not all of these generalizations to more relational structure, are on a par. And so that's a thought that actually belongs to, again, the mathematician Polya, who writes, there are two kinds of generalizations, really. One is cheap and the other is valuable. It is easy to generalize by diluting a little idea with big terminology. It is much more difficult to prepare a refined and condensed extract from several good ingredients. All right, so in a way, the distinct kind of analogical arguments that we discussed for the very same conclusion seem to indicate that this difference between condensing and diluting is an important one to keep track of when we consider the pedagogy of mathematics. Perhaps the thought that we have here can be summarized in the following terms. If the psychological theory is insecure or incomplete, or maybe needs to be improved for taking into account this other aspects that we're mentioning, then perhaps the history of science and the history of mathematics can be consulted as an alternative basis for pedagogy. And here, of course, we face the usual problem that some people have called the learning paradox. That is to say, if one tries to, as Beriter says, if one tries to account for learning by means of mental actions carried out by the learner, then it's necessary to attribute to the learner a prior cognitive structure that is as advanced or complex as the one to be learned. Now, this is a problem for two kinds of very broad approaches in pedagogical practice. One is the so-called representationalist approach, which kind of focuses on the metaphor of learning as a kind of perception of external representations. This is a problem because, as Holt and others describe in this famous experiment of comparing numbers and roads, Bill and I could see a strong connection between the word of rods and numbers. We therefore assumed that children, looking at the rods, could see how the word of numbers worked, so how the operations between numbers worked. And that experiment totally failed, precisely because, as it were, the way students construct things, mathematical notions, is not in the way of perception. So teachers should not just assume, as it were, that students see the properties or the commonalities, as it were, that the teachers have in mind when they present them with a problem. It is also, at the same time, the learning paradox, a problem for constructivism, which understands that, as it were, the mathematical properties are, in a certain sense, constructed. They're not an object of a special kind of intellectual perception, but they have to be constructed by the students in relation to their teacher. Because it's a problem for this, because as Brousseau says, the more explicit I am about the behavior I wish my students to display, the more likely it is that they will display that behavior without recourse to the understanding which the behavior is meant to indicate. That is to say, the problem is that if we just tell the teachers, okay, you have to bring students to understand the comparison between two domains. You have the students to put the students in a position to be able to make sensible inferences from one domain to another. Then the more, as it were, the students, the more the teacher intervenes in this pedagogical experiment, the more the students are going to display the relevant behavior, making projection, making analogical inferences, without understanding, really understanding the subject. Okay. So, well, how do we get out of this learning paradox? Well, one way is just to say, well, let's give up. The dilemma cannot be overcome. We cannot accelerate the process of developing analogical thinking nor contribute to its development. However, that would be a kind of a very bad defeat in a way. As Polya, for instance, had noticed, mathematics seems to offer a very privileged way or arena for thinking about analogical reasoning and its virtues and limits. So if we give up on trying to teach students analogical reasoning in mathematics, problem solving, then roughly we might end up with problems for teaching analogical reasoning in more generally, in science more generally. And so we have to give up on certain kinds of relevant capacities that are associated with analogical reasoning, among which the capacity to see something as something else, the capacity to sort of reflect on one's inferences, inductive inferences, and to reflect on the trustworthiness of models, and also the capacity to develop a better appreciation of science and mathematics, right? Because, as I mentioned at the beginning, both science and mathematics, in both of these disciplines, as it were, analogy plays a rather prominent historical role. And so how are we going to do this? How are we going to escape the learning paradox and sort of pursue a coherent line of teaching by analogy? So that's the kind of question that we're starting to investigate with Nicolò, and that Nicolò will talk about briefly now.
Thank you, Francesco. So, okay, in this last part of the talk, I try to explain in 20 minutes, something like that, how it's possible to exploit the deep connection between the students and the researchers. In particular, here I'm referring to the parallelism that can occur in the activity of puzzle solving, for instance. Because, as Francesco said, we based our idea on the comparison between the pedagogical growth of the students in the middle school as well as in the high school, and the epistemological growth of the science in the history. So far is precisely this role of the history in the mathematical discovery, in the mathematical science, in mathematical discovery, that seems missed in student education, and also is a possibility to use this kind of practice to better try to create a new form of teaching and learning. In particular, in our approach, we try to overcome the criticism that Francesco exposed a few slides before by a new kind of representation in teaching and learning. On the one hand, representationalism lacks in considering social and contextual dimensions, so the historical dimension of the problems. On the other hand, constructivism leads most of the time to merely reproductive usage of student imagination. Sometimes we have no creativity usage for the students when we talk about constructivism. And so our aim is to nudge the students while making their circumstances as close as possible to the researchers. In particular, this includes motivational aspects, for instance, priority rules, and as well as the presence of peer review-like processes. So in the next slide, I try to explain some application that we have tried to develop it here in the Politecnico Milan, thanks to the Laboratorio FDS, which is a laboratory of mathematical learning, mathematical teaching, mathematical outreach. And in this context, we are trying to make some exercises in as a part of a bigger context. Indeed, we are organizing for the Pi Day on the 14th of March a mathematical escape room online, which is a mathematical game for mid and high school students. And this game will be composed of 6 different rooms corresponding to 6 different kind of mathematical questions. The students will have an hour to solve all these conundrums. And the competition will take place online and involve schools from all over Italy. The choice of this particular structure, I mean, the game is interesting because it allows us to experiment some possibility also for analogy linked to learning, but also, as I said, teaching a process in a way that could also see, well, we hope, stimulating for most of the students. And just one more precision in the explanation. I omit the specific details of the creation of the world regarding the escape room, the imaginary world in the creation of the escape room. And just concentrate my explanation on the mathematical challenge and the role of analogy in the mathematical challenge and the analogical reason that we hope to induce to the students. Okay,